everybody, and this is joint work with Anna Carlin, who's here, and Hu Fu, who is right over there. Okay, so I'm going to talk about mechanism design. So let's start with the standard model for mechanism design. There's a seller offering goods or services, and for most of this talk, I'm going to assume that the seller has one item to sell. And there are buyers with known values that arrive and are interested in buying this item. And we want to design an auction or a mechanism for this where the seller, which takes in as input the buyer's values and returns an allocation of the item or items, and also a price to charge each buyer. And our goal for this talk is to maximize the seller's revenue. Okay? And typically, we assume in the setting that the seller has some Bayesian information about the buyers, so he knows the distribution from which the values are drawn, and can use this in designing an auction. Okay? Now, in many realistic settings, this model is actually not completely relevant, and I like to think of the situation where there's a house for sale, and buyers arrive, and then they look at the house, they get get it inspected and so on, and they use all of this information to get the best idea they can about their own value, but they might not know their own value perfectly. This is some function of what they observe, and also some function of what other people observe. Okay, and I'm gonna call this model the interdependent values setting. And let me define this sort of model precisely. This formalization is due to Milgram and Weber. So here, each buyer now obtains some signal about his true value for the item under sale. And these signals are drawn from some joint distribution. They could be correlated or not. And then the value of a buyer is a function of all of these signals. Okay? And for most of this talk, I'm going to assume that this is a function of this simple additive form. Much of the work in this area, in fact, applies specifically to this format. But in fact, our results will apply a little more generally, so I'll talk about that later. But let's assume that this value, let's assume for now, that it's some additive function that depends on each of these signals in some manner. Okay? And also, just as a sanity check, we're going to assume that the signal is positively correlated with the value. So VI is a non-decreasing function of the agent's own signal. Okay, and the question we want to ask is, so now informationally the setting is a little bit different, and we want to ask, well, how do we design a mechanism for this sort of setting? Okay. Now note that one primary difference between this setting and what we saw before is that the buyer starts out with some limited information about his own value, and through the course of the mechanism might learn more and more and update what he knows about his own value depending on what he learns about other people during the mechanism. So there's a question of what we mean by incentive compatibility in this context, and we're going to use the strongest possible version of incentive compatibility, which is ex post incentive compatibility. We'll say that the buyer is satisfied reporting his information even after he has observed everything there is to observe about other people's signals. Yeah.
You're assuming the signal is a real number. Is that without loss of generality?
That is not without loss of generality, but we will assume that. So we're talking about every agent being a single parameter agent. So so for most of the talk, we will talk about there being a single item for sale, in which case it sort of makes sense that the signal captures the buyer's best information at the beginning of the mechanism about his own value.
But even if there are settings with a single item, you can imagine a signal which is not...
That is multidimensional in some sort. Yeah, but here we will assume that the signal is single dimensional, and I don't think that's without loss of generality. Okay. So we will use the concept of ex post IC. And in this talk, I want to ask the question of how you maximize revenue in this setting, and we will present an approximately optimal mechanism for this problem. Okay? So before we talk about revenue, let's try to understand what happens when you're trying to maximize welfare, just to get a hang of this setting. So so we're trying to maximize welfare, and in independent value or in the standard setting where the buyers all know their values, the VCG mechanism maximizes welfare. In this interdependent setting, there's a very natural generalization of VCG, and that's the following. So you ask all the buyers to report their signals, and then use this information to compute everyone's values using the known value functions. And then we allocate the item to the buyer that has the highest value. And the question is, how much should you charge this buyer? In the case of the private values setting, we typically charge the buyer his critical value, which is the smallest value that the buyer would have needed to report in order to win the item. There's a natural analog here. You could talk about the buyer's critical signal, which is the smallest signal that the buyer would need to report in order to win the item. And what you could do is to charge the value of the buyer at that critical signal, given everyone else's signals. Okay? So it's a natural generalization of the Vickrey auction. We will call it the generalized Vickrey auction. I'm sorry, what's that? There isn't an ordering on signals. Everyone reports their signals, and for the winner, you could ask, well, what is the smallest signal this guy needed to report in order to win the item? So there is a problem with this auction, and some of you have already sensed that, so let me get to that. So first, pictorially, what is this doing? So let's imagine you have two buyers, and let's say that the first buyer is the one that has the higher value. Now let me plot the values of the two buyers as a function of the signal of the first buyer. And let's say these values, they look like these functions of S1. So I'm fixing the second buyer's signal here. And our definition of critical signal is this point where the first guy's value crosses the second guy's value. Okay, so this is the critical signal, and this is the price that we will sell the item at to the first guy. Okay? Now, there's an immediate problem with this, which is that it could be the case that these value functions cross at multiple places, in which case now, the question is, how do we define the critical signal? The Vickrey auction or generalized Vickrey auction would want to sell to the first guy at this signal and at a signal over here, but would want to sell to the second guy if S1 is over here. Okay? And if we run this generalized Vickrey auction, it's not going to be ex post incentive compatible. So we're going to take the easy way out here. We're going to assume that the value functions satisfy the property that for any S2, if you look at the values as a function of S1, they only cross at one place. Okay, and this is a standard assumption in all of the work on this model. An open question here is to think about what to do when single crossing doesn't hold. So we will also make the single crossing assumption. Yeah.
So can I interpret this as saying that I'm more sensitive to my own signal as it gets larger?
That is a more restrictive condition. Certainly, if that were the case, that would imply single crossing. But you might have single crossing even if that's not the case everywhere.
In the absence of this assumption, is it not known whether there is a welfare maximizing incentive compatible?
So in the absence of this condition, any auction that tries to maximize welfare ex post is not going to be ex post IC. You could still ask the question of what if I wanted to maximize welfare and expectation, and that has not been studied to my knowledge.
So what's wrong with just using the first crossing?
Well, it's not going to be, so if you want to always allocate to the person that has the highest value, then over here, when S1 is right here, you want to allocate to the second to V2 here. Okay, because V2 is more than V1. And so if you use this as the critical signal, then this is not truthful. This is not exposed IC. So increasing the buyer's signal, alternates who gets the item. Any other questions before we move? Okay. So we're going to make this assumption, and now we want to move forward to revenue maximization and ask, how can we maximize the expected revenue for this setting? Okay. So it's instructive to think about the special cases of this problem that we know how to solve. So one special case is, of course, the independent values setting, where every agent's value is drawn independently from some distribution, and every agent knows their value at the beginning of the mechanism. And in this case, most people, I expect in this room, know that Meyerson designed a mechanism that maximizes revenue in this case. And essentially what this mechanism does is to express the expected revenue as a sort of expected virtual surplus, and then maximize this virtual surplus. Okay? Another special case that we understand of this problem is the case where buyers' values are private, so they know their value at the beginning of the mechanism, but they're correlated, drawn from some joint distribution. And in this case, Ronen designed a mechanism which gives an approximation to the revenue. And this mechanism is essentially a sort of victory with reserves mechanism. So it's a victory auction that sets an appropriate reserve price for the agents, and then it can obtain a constant fraction of the revenue. Okay? So we could start, in order to approximate our general problem, we could start with one of these two approaches and try to see how far we get. And so our first try is to start with the expected revenue objective and try to express it as a virtual surplus. And this can indeed be done, and a number of papers have tried this approach. The problem with this approach is that the virtual value functions are not quite as nice as in the independent setting. And in order to extract an exposed IC mechanism from this, one has to make a number of different assumptions that the virtual value functions have to satisfy. And the most general result in this setting is due to Tim and Inbal. And they show that under different assumptions, one can try to maximize virtual surplus, so compute everyone's virtual values, allocate the item to the person with the highest virtual value, and this maximizes the expected revenue of the mechanism if it turns out to be exposed IC. Okay, I won't describe these assumptions, but they include, for instance, symmetry across agents, a generalized version of the monotone hazard rate assumption, regularity, and so on. Okay, so second try is to go with the generalized victory with reserves set appropriately. And this has also been considered before in the paper by Roughgarden and Thalgum-Cohen, and also a paper by Lee. And indeed, this works out under certain assumptions, such as symmetry. I mentioned generalized MHR before. So under these assumptions, this leads to an approximately optimal mechanism. However, once you remove these assumptions, this sort of approach can be arbitrarily bad in general. And I'm going to show an example shortly for where this approach fails. Okay? So, so the question is, what do we do? What is the third approach that we can follow? So in the rest of this talk, I'm going to talk about Ronen's approach for correlated values. We'll see why Vickrey with reserves works in that setting, and we'll see why it fails in the more general interdependent setting. And looking at that example will suggest a natural modification, and it turns out that that will work generally and give us an approximation. Okay, so I should thank Hufu for these nice pictures on the next few slides. So let's think about the setting where every buyer has private values, but these are drawn from some arbitrary joint distribution. So here are a bunch of agents, and they're competing for an item under sale. And what Ronen wants to do is to allocate this item to the person that has the highest value. Okay, in this case, it's this guy. Okay, and so the question is, how much should we charge this guy for this item? Okay, now we want the mechanism to be IC, and so we're going to use everything that we know about his value except for his own report. Okay, and so we'll ask everyone else to report their values, and we will condition on all of these reports that we receive, and we will use these to construct a conditional distribution over this guy's value, and then we will choose the best reserve price for this distribution and offer the item at that price to this guy. Okay? And this is called the look-ahead auction by Ronen. It's essentially the Vickrey auction with reserves. Okay, so let me prove to you that this auction gets good revenue. And we're going to do this as follows. So we want to relate the revenue that this auction gets to the optimal revenue that it could have received. So let's break up the optimal revenue into these two components: the amount that the optimal auction gets from everyone but the highest value guy, and the amount that it gets from the highest value guy. Okay. Okay. Now, we did the best possible thing for the highest value guy. Given that we wanted to be ex-post incentive compatible, we offered the best possible price for the item to this guy. And so, in fact, this component of the optimal revenue is no more than the revenue that the look-ahead auction gets. But on the other hand, the most revenue we can get from these guys is the most value for the item that any one of them has. Okay, and we could always have charged this price to this highest value guy because this value is greater than that price. And so, in fact, this quantity is also no more than the revenue that the look-ahead auction gets. Okay, and so that proves that opt is no more than 2 times R, and so the look-ahead auction gets at least half the expected revenue of the optimal auction. Okay, and this turns out to be tight. Okay. Okay, so what happens when people's values are interdependent through the signals that they receive? So I'm going to claim that if your mechanism was only ever selling to the highest value guy, then it cannot always guarantee a good fraction of the optimal revenue. Okay. And here's an example for that. So here's a setting where we have a single item and 2 people, 2 buyers. And the first guy is going to get a signal that is drawn from the equal revenue distribution. Formally, it's this distribution. The probability that the signal is greater than x is equal to 1 over x. And this is also going to be this guy's value. Okay, so the first guy observes his value exactly. The second guy observes nothing, but his value is just a shade lower than the first guy's value. So it depends solely on the first guy's signal. Okay? Okay, so what would selling to the highest valued agent do here? well, the only thing you can use is your knowledge that his signal is drawn from the equal revenue distribution. We don't benefit at all from seeing the second guy's signal, because the second guy doesn't get a signal. And so the best thing you can do by selling to buyer one is to get a revenue of $1 here. Whereas, what would the optimal auction do? Well, it's getting perfect information about the second guy's value by observing the first guy's signal. So, in fact, it can charge the second guy exactly his value and still be incentive compatible and gets unbounded revenue and expectation. Okay? So this is like a trivial example. In this setting, we know exactly what we ought to be doing, but selling to the highest value agent is not a good idea. Okay, and let's look at where Ronen's argument fails. So Ronen's argument in the correlated private values setting used the fact that we can always extract at least as much revenue from the highest value agent as the second highest guy's value, okay, in the private values setting. Here, what happens is the second guy's value changes if the first guy's signal increases. And so the first guy's signal might be out here, and the second guy's value might be much larger than the price that we can charge at the critical signal to the first guy. So we're giving up on all of this value by charging the highest agent his value at the critical signal. Okay? And for this example, what we ought to be doing is to immediately eliminate buyer one from the auction and then just sell to buyer two. Okay? And I'm going to prove to you that this is essentially all you need to do to Ronen's mechanism to get approximately optimal revenue in general. So here's the mechanism that we'll use. In the paper, we call it Vickrey with admission control. Here, I call it Vickrey with random rejection. I don't know if either of those names are really good for this. But basically, what we do is, in the first step, we just reject any buyer independently with some probability. Here, I'll use 1/2. And then over the remaining set of agents, we're going to run Ronen's mechanism, which is generalized Vickrey with an optimal reserve price. And I picked the optimal reserve price looking at everyone's reported signals, the guys that survived the first step and also those that don't survive the first step. Okay? And in my remaining 7 minutes, let me prove to you that this is approximately optimal. So again, let's look at the picture with 2 buyers. So here, let's suppose that buyer 1 has the higher value at the reported signals, and here again we have the values as functions of S1 with S2 being fixed. So the optimal mechanism gets some revenue from the highest value buyer and some revenue from the second buyer. And I'm going to think of the revenue from the second buyer as being composed of 2 parts. The second buyer's value at the first guy's critical signal, and whatever else he gains by the first guy's signal being larger than his critical signal. Okay? Now, what does our mechanism get? Well, as before, if it's the case that both these 2 agents survive our first random rejection step, then we do the best possible thing for the highest value guys. We get H in that case. And that takes care of this component. It also takes care of this component, just as in Ronen's argument, because we charge at least L2 to the highest value guy. And I'm going to next prove that in the case where 2 survives the first step, but 1 doesn't, we get at least L1, okay? And in that case, we can put everything together and get, for this mechanism, an 8 approximation, and we can adjust the probabilities a little bit to get a slightly improved 4.5 factor. Okay, so let me prove this claim now. So if the second highest value guy survives the first step, the highest value guy doesn't, then our auction gets at least this L1 quantity. And here I'm going to recall our assumption that V2 is this sort of a sum of functions of the signals of all the agents. Okay, so what's happening here? So in the second step, we are conditioning on the first guy's signal and computing the best possible price for the second highest guy. And this best possible price is going to be at least this component of his value, G12 of S1. Okay, we can charge at least this much because we know his value is at least so much, and we might be charging something higher. But note that this component captures also this change in V2 if the signal S1 decreases from this level to this level. Okay, and so this price that we charge is at least L1, and that's it. Okay, in other words, here this is the change in V2 due to the first guy's signal, and we should be able to get at least so much by looking just at the first guy's signal and nothing else. And oops, sorry. There we go. Okay, and in fact this holds more generally assuming a certain condition on the second derivative of the value with respect to the buyer's own signal and anyone else's signal. Okay, so before I can move forward, let me give a quick comparison of where this result stands relative to two other recent results on the interdependent model. So one is the optimal auction due to Tim and Inbal that I mentioned a little while ago, and another is an E approximation via Vickrey with reserves due to Lee. So we get a worse approximation factor than either of these. We require a single crossing, but then we require a milder condition on the value functions than the optimal auction does, but this one doesn't require any condition on the value functions. And on the other hand, both of these mechanisms require a number of conditions on the value distributions, and our approximation doesn't require any assumptions on the value distribution. So this is one strength of the approximation. Okay, we can extend this mechanism to other single parameter settings. So one natural extension is to settings with a matroid constraint. So here we can simultaneously serve sets of agents, and I won't define what matroids are. Most of you perhaps know already, but two natural examples of matroids that arise are k-unit auctions, and if you have a matching between agents and items, then this naturally defines a matroid over the sets of agents that can be matched to items on the other side. And so these are natural settings where this might arise. So for matroids, our mechanism is pretty much the same. Again, we in the first step, we just reject every agent independently with a probability of 1/2. And then for whoever survives, we run a generalized VCG mechanism with reserves, where we first pick the set of, we compute everyone's values. We serve the set that has the maximum total value in it, and for every agent in that set, we set an optimal reserve price depending on all of the information that we've seen so far. And that mechanism obtains a constant factor approximation to the optimal ex-post IC revenue. Okay. And beyond matroids, it turns out that generalized VCG is no longer ex-post IC for a reason that's similar to why it's not exposed to IC for settings that don't satisfy single crossing. And so again, in this case, we don't even know how to maximize expected welfare. Presumably, if we can figure that out, that ought to lead to a good mechanism for revenue as well. So that's a natural open question. So to conclude, we come up with a reasonably simple constant factor approximation, and the strength of it is that we need mild assumptions on the value functions. We don't need any assumptions on the value distributions, and so it greatly simplifies what we can do in this setting. Okay, thanks. Questions?
Time for a few questions while Hannah sets up. Next up.
Yeah.
Comparison slide with Tim and Impal's work, the cross-function derivative, it looked like it was split between yours and Tim's work, right?
That's right. That's right. Yeah. Yeah. So they're sort of incomparable. Yeah. They. But you know, when you have so if the value function is the sort of additive function over signals, then both of those second derivatives are 0. So. Yeah, so that satisfies both of those conditions.
More questions?
Yeah.
So this was requiring that like the API SI for anybody else's signal and your value was positive?
So your own signal is positively correlated with your value, but the others don't have to be. Actually,
I thought when you were conditioning on the other value and talking about the difference in between, that required that to be positive.
Well, if it's negative, then you really don't lose that term. Yeah, yeah. So it doesn't have to be positive. Yeah, or it doesn't have to be non-decreasing. Yeah. Yeah.
But the pure common value setting where each agent gets the unknown value plus, let's say, Gaussian noise?
It does. In fact, there things should be even simpler for revenue maximization.
So this is non-crossing, right?
That's right. Yeah, yeah.
I mean, single.
That's right. Yeah, it satisfies single crossing.
Do you know any results for multidimensional settings? And also, I was confused about the discussion of welfare. What do we know about welfare?
So what we know about welfare is that under single crossing, generalized VCG is, it ex post maximizes welfare, so it's optimal, and it's also ex post IC. Multidimensional, I haven't seen a reasonable model for it, so I don't know. You'd have to, come up with a reasonable model first. So, yeah.
So let's take other questions offline.